Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic and gives you more tools for doing things with proofs. I introduced a variety of conventions in the previous video, things that allow us to make explicit the modal steps while in a sense suppressing the propositional steps. We are allowed to write down theorems that we've already proven without having to reprove them. We are allowed to write down substitution instances, either propositional tautologies or the K axiom or theorems that we've already proven without first writing that theorem down. We will suppress certain types of propositional reasoning instead of putting in a substitution instance of, say, an embedded conditional and then doing a bunch of modus ponenses. We'll just put down the consequence, so the result of having done the modus ponens. And all of these things will allow us to have simpler, more effective, and easier to read and understand proofs. In this video, I'm going to, first of all, show you how that works for a very simple theorem, and then give you another way that you can essentially skip steps in your proof. And this is through the notion of a derived rule. So just as in propositional logic, derived rules and modal logic don't allow you to prove anything new. They just allow you to prove things in fewer steps because there's certain proof patterns that you would always be replicating, and the derived rules allow you to just kind of elide them and say, look, okay, this is what the steps would look like to get from here to here. So we prove the rule once, and then after that, we just go from the first to the last and skip all the steps in between, essentially telling the reader, if there's any point at which you would really like to see these steps fleshed out, go and reference the proof of this derived rule and you will be able to reconstruct the steps. So there we have it. So let's get up my whiteboard. The theorem I'm going to give you is, we're going to label it K3 because it's our third theorem in the system K. And that is that if we have necessarily P and Q, we have this if and only if necessarily P and necessarily Q. So using all of our proof conventions, this becomes very, very easy. First, we have that necessarily P and Q implies necessarily P and necessarily Q. And this was our first theorem. This was K1. And then the converse of it, that necessarily P and necessarily Q implies necessarily P and Q, is our second theorem, K2. Now, propositional logic says if you have two conditionals, one of which is the converse of the other, then you can put them together into a biconditional. Now, we could do some sort of propositional tautology, say if P implies Q, then if Q implies P, then we have Q if and only if P. We could do the substitution instances and two instances of modus ponens, or we can just go directly to the biconditional. So what would otherwise have taken us probably around about 15 to 20 lines if we replicated the entire proof of K1 and the entire proof of K2, and we put in this propositional tautology, took a substitution instance of it, you can see that none of those steps are particularly illuminating as to what's going on at the level of modality. So here is our simplified proof given our convention. Now, the first derived rule that I'm going to give you is Derived Rule One. I know, what a great name for it. We will abbreviate it DR1 when we want to. This rule says that if you have proven some conditional, so you've got a conditional as a theorem, then you will be allowed to write down that conditional with a box on the antecedents and a box on the consequent. So why are we allowed to do this? This is because, well, suppose that you have a proof that of some conditional. So it's not going to be step one of your proof. It might be further on down. It doesn't really matter. I'm just giving you the steps that get you from the conditional, which we're taking it as given that you have, to the version with the boxes on it. Rule of necessitation allows us to put a box on the front. So this is rule N applied to line 1. Then we have a substitution instance of the K axiom. So what I'm doing here is I'm just substituting phi for P and psi for Q. And then, of course, we've got modus ponens that takes us from necessarily phi implies psi to necessarily phi implies necessarily psi. So that's modus ponens 2 and 3. What derived rule 1 does is allow you to ignore these 2 steps and not actually have to do them. So you can go straight from 1 down to 4. So it doesn't remove a lot of lines from our proof, but it does remove kind of steps that aren't illuminating. So if we have a conditional that we've proven, we know it's a theorem, then we can stick boxes on the front of both and just move down. And in fact, you can very easily get another derived rule. And this is going to be, clear away all of that bits. We don't need it. I'll give you derived rule 2 really quickly because it's very easy. Derived rule 2, DR2, says that if you have proven some biconditional, then you can put boxes on both sides of the biconditional. And again, we start off by saying, okay, take the biconditional as given. Well, we know that this is the same as having the conditional in one direction and the conditional in the other direction. But derived rule 1 says that we can put boxes on the front of both of these. So derived rule 1 applied to line 2, and then derived rule 1 applied, there we go, that's a phi, to line 3. And propositional logic says if you've got 2 conditionals, one of which is the converse of the other, you could put them together as a biconditional. So at this point, sorry, that's propositional logic 4 and 5. At this point, you can now see that this is a rule that actually removes quite a lot of steps because we're going straight from 1 until 6. But derived rule 1 and the applications here elided 2 extra proof rules. So if we had spelled out all of these, this would end up being quite a clumsy and clunky sort of proof to go through, when really what matters from the modal point of view is that if you have a biconditional between 2 things, then just as they're going to both be true together or both be false together, they're also going to both be necessary together or not necessary together. And that's all that derived rule gives us. So derived rules are super useful, and we'll look at another rule in the next video, which is a little bit more complicated, but also makes things so much easier. So join me next time for substitution of equivalences and another derived rule. Take care and see you later. Cheers.